Hello guys, here are the calculations on resonance tube. So here we're going to apply what you have learned in the previous video on the formula we use to calculate the velocity of sound in air using what? Resonance tube. The question 1 says, a tuning fork of frequency 600 Hz, this is sounded over a closed resonance tube. If the first and the second resonant position are 0.130 meter and 0.413 meter respectively, calculate the speed of sound in air. So when you set the resonance tube, the air column into vibration with the help of this known frequency tuning fork. The first point where the resonance is set up or occurred is your L1, which is this. While the second position is what? L2. As you let the water out of the resonance tube, you have second resonance position. So from the question I can say, here is my L1, here is what? L2. Here is the frequency of the tuning fork. Are we clear? So remember the formula we generated, that V is equal to 2F into L2 minus L1. If you have not watched the video on the explanation on forced vibration, resonance, and resonance tube, where we derive this formula, ensure you watch it before coming to these calculations. So here now, I have all I want. I have F, the frequency of the tuning fork, to be 600 Hz. I have the first resonant position, L1, to be 0.130 meter. Second resonant position, L2, 0.413 meter. So what am I looking for? V. So from that, this is going to be 2 multiplied by F, 600, into L2, 0.413 minus 0.130. By the time I multiply this, I have 1,200 multiplied by the differences of 0.413. That will give us 0.283. So when you multiply it together, that will give us 339.6 meter per second as the velocity of what? Of sound in air. So this is how to approach this type of question. Let's move to the next question. Looking at the next question, it says, in a resonance tube experiment, if the fundamental frequency of the vibrating air column is 280 Hz, the frequency of the third overtone is? Very simple and straightforward question. We're looking for the frequency of the third overtone. There are videos I have done on overtones for a closed pipe and an open pipe. There, if you watch it, you see that this question is a very straightforward question. So let's itemize what we have. We are given the fundamental frequency F0 to be 280 Hz, and you are looking for the frequency of the third overtone, right? Frequency of the third overtone. So our resonance tube is treated as a closed pipe. Is that clear? So in a closed pipe, we have the harmonics generated are odd, right? The first harmonics is your fundamental frequency, right? The second harmonics is your first overtone, so we call it first overtone F1, right? First overtone is F1, which is the odd integral multiple of the fundamental frequency, which is, in that case, we have 3F0. The second harmonics, the third harmonics, which is your second overtone, that is F2. The second overtone is equal to 5 F naught. Are we clear? The third overtone, which is your fourth harmonics, third overtone F3, is equal to 7 F naught. Then fourth overtone, which is F4, I believe you know the next one is odd, right? Is going to be 9 F naught. But the question is talking about what? Frequency of the third overtone. So we are referring to this. Are we together? So frequency of the third overtone F3 is equal to 7 F naught. Right? Please ensure you get this. You familiarize yourself with this so that you don't need to draw the standing wave pattern before you can be able to solve this a simple question. You know, this question is just for you to say 7 multiplied by this. But if just remember one thing, that in a closed pipe we have odd set of what? Overtones. First overtone is 3 times of what? Fundamental frequency or first harmonics. Second overtone is 5 times. The next odd number after 5 is 7. The next odd number after what? After 7 is 9, and so on. So here is your first 3, second overtone 5, third overtone 7, and so on. But in an open pipe, we are having even number. It contains all the harmonics. You have F naught, 2 F naught, 3 F naught, 4 F naught, and so on and so forth. So here is our fundamental frequency, the first harmonics. Here is the second harmonics, but first overtone. Here is the third harmonics, but what? Second overtone, and so on and so forth. Are we clear? So from here, we now have that the third frequency of the third overtone is 7 multiplied by 280. That will give us 1960 hertz. As simple as this. I hope it is clear. The next question says, if the first position of resonance in a resonance tube is 18.0 centimeter from the open end, the distance from the open end to the next position of resonance will be, so we're looking for what? Remember, now, the first position. I still leave this diagram for better understanding. The moment you get the scenario behind everything like this, you don't need diagram again. You will just from question you'll be able to know what they are referring to. So the first position we're talking about here said the first position of the resonance in a resonance tube is this. That is to say, we have L1 is what? 18.0 centimeter. Correct? From the open end. The distance from the open end to the next position, here is the next position, right? The second resonance of resonance will be, I'm looking for L2. Looking for what? L2. So this is another kind of problem. How do we approach this? We know from this that the fundamental frequency here, the first length of the air column at first resonance, L1 is equal to lambda over 4. In that case, if you put the value of L1, you have 80 is equal to lambda all over 4, such that lambda is equal to, by the time I cross multiply, lambda times 1 is lambda, 18 multiplied by what? 4. Gives us 72 centimeter. So I'm looking for L2, but the second resonance, we have that L2 is equal to 3 lambda all over 1, 4. Is that correct? So this will be equal to 3 multiply, what is my lambda? Lambda is 72, then all over what? 4. That will give us 216 over what? 4, which is equal to 54 centimeters. Is this one clear? See the approach to this type of question. The next question says, in a resonance tube experiment, a tube of fixed length is closed at one end and several tuning forks of increasing frequency used to obtain resonance at the open end. If the tuning fork with the lowest frequency which gave resonance had a frequency F1, and the next tuning fork to give resonance had a frequency F2, find the ratio F2 to F1. In this type of question, it's very simple. Don't panic with the lengthy write-up. Just read through and extract your data. Here we don't have numerical data, we're looking for the ratios. So remember, we treat resonance tube as a closed pipe. In a closed pipe or in a resonance tube, the point where we have or where the first resonance occurred is at the fundamental frequency at first harmonics. And the first frequency, fundamental frequency, which is the first harmonics, F naught, here is the same thing as what? F1 is equal to V all over 4L. There is a video where I discussed the formulas, I derived the formulas for standing wave pattern in a closed and open pipe. There you learn this, how we come about this fundamental frequency equal to V over 4L. I hope it is clear. So the second resonance, right, will be at this level where we have our second frequency F2 will be equal to 3V all over 4L. So we're looking for F2, ratio of F2 to F1. This implies we have F2 to F1 will be equal to, what is the value of F2? 3V over 4L, 3V all over 4L, then all over F1 is what? V all over 4L. This is a division of fraction by fraction, so this will be equal to 3V over 4L. Then this division line, the big division will turn to multiplication, then the fraction at the denominator will reciprocate. The denominator will become what? Numerator, and numerator becomes a denominator. So I have 4L all over V. So the V here, we cancel the V at the numerator. Same goes to 4L here, 4L here. This will now give us 3, which we can rewrite as 3 over 1. This implies that F2 to F1 is equal to 3 all over 1. Therefore, F2 ratio F1 is equal to 3 ratio 1. So, in your options, you might see 3, that is 3 over 1. You might see 1 over 3, so the correct answer there is what? 3 or 3 over 1. Are we clear? This is how to approach this type of a question. So here is our next question. The question says, in a resonance tube experiment, the frequency of the tuning fork is 750 Hz and the resonating length of the air column is 0.3 meter as shown above. The velocity of the wave is, look, assuming we don't have this here, we only have this question here. From the previous understanding of my tutorial, you should know that this is what? A second resonance, second position of what? Of the resonance. Are we clear? So if that is the case, remember here we are not giving a two situation where they talk about the first and the second. We are only giving only second resonating position, right? So here we're not going to use V equal to 2F L2 minus L1, no. Rather, we consider the fact that the frequency of the tuning fork is, for it to be at resonance, is in coincidence with what? With the frequency of what? Of the vibrating air column. In that case, this frequency of the tuning fork is the same thing as the second frequency or resonance frequency of the air column. And if you watch my previous video, we have that the second resonance, which is the second harmonics, is equal to 3V all over 4L. The first harmonics, or the first fundamental frequency, which we use F0, is equal to what? V over 4L. The second one is 3V over 4L. Are we clear? If that is taken, here we have our frequency is 750 equal to 3V all over 4 multiplied by length of the resonating air column 0.3. Are we together? So by the time I cross multiply, I have 3V is equal to 750 multiplied by 4 multiplied by 0.3. So which implies 3V is equal to 900. Right? So divide both sides by 3. I have 3V all over 3 is equal to 900 all over what? 3. 3 cancel 3. I have V is equal to 300 meter per second. So this is the velocity of what? Of the sound wave.